Welcome to Principles of Ecology. Today, we are diving into a fascinating topic that explains exactly how predators and prey interact in the wild. We will explore functional and numerical responses. By the end of this video, you will understand not just how individual predators hunt, but how entire populations respond to changes in their food supply. Let us get started. Before we look at the formal ecology, let us build our intuition with a simple analogy. Imagine you are at an all-you-can-eat pizza buffet. If there is only one slice hidden away, you eat slowly because finding it takes time. But if the staff brings out 100 slices, your eating rate skyrockets. However, eventually, your stomach gets full. No matter how much pizza is there, you can't eat any faster because you need time to chew and digest. In ecology, this change in an individual's eating speed based on food availability is called a functional response. Now, imagine your friends hear about the buffet and rush over to join you. This increase in the actual number of eaters is called a numerical response. Building on our buffet analogy, let us formally define how a predator spends its day. Predators divide their total foraging time into two distinct activities: search time and handling time. Search time is exactly what it sounds like, the time spent actively looking for food. Handling time is the physical time required to catch, kill, eat, and digest a single prey item. As prey becomes more abundant in the environment, the search time drops to near zero because food is everywhere. However, the handling time per prey item remains constant. You cannot chew any faster. This creates a physical bottleneck that limits the maximum possible consumption rate. Now that we understand this physical bottleneck, let us look at the formal ecological definitions. The functional response describes the relationship between the per capita predation rate and prey density. Simply put, it measures how many prey items a single predator consumes per unit of time as the prey population changes. The famous ecologist C.S. Halling categorized these into three main types. Type 1 is a linear increase. Type 2 is a decelerating curve that hits a plateau due to handling time, just like getting full at the buffet. And type 3 is an S-shaped curve, where learning or prey switching occurs. While the functional response looks at the individual, we must also consider the whole population, which brings us to the numerical response. This describes the change in the predator population density in response to changes in prey density. This happens through two primary mechanisms. First is a demographic response, where predators reproduce more and survive better simply because they are well fed. Second is an aggregative response, where predators physically migrate into areas where prey is abundant. Together, the functional and numerical responses determine the total predation pressure on a prey population. Understanding both of these responses is not just academic, it is absolutely critical for real-world applications, like wildlife management and agriculture. For example, if farmers release ladybugs to control a sudden outbreak of crop-destroying aphids, they need to know if the ladybugs can eat enough aphids to stop the swarm. If the ladybugs have a type 2 functional response, they might get full too quickly and hit their eating plateau. Furthermore, if they do not reproduce fast enough to create a strong numerical response, the biological control will fail. Conservationists also use these concepts to predict if endangered prey will be hunted to extinction. To make these concepts useful, we need to translate them into mathematics, which leads us to Halling's disk equation. This formula perfectly describes a type 2 functional response. It accounts for the fact that predators cannot spend all their time searching. They must also spend time handling their food. In this equation, NE represents the number of prey eaten by a single predator. The symbol A stands for the attack rate, measuring search and capture efficiency. N is the prey density, and T is the total time spent foraging. Finally, H is the handling time, which is the time it takes to catch, kill, eat, and digest a single prey item. If handling time increases, the total prey eaten will decrease. Now that we have our formula, let us apply it to a practical scenario involving a spider hunting flies. We are given an attack rate of 0.1, a handling time of 0.5 hours, a total time of 10 hours, and a prey density of 20 flies. We want to find out how many flies the spider will eat. First, we calculate the numerator, representing maximum theoretical encounters. Multiplying the attack rate, prey density, and total time gives 20. Next, we calculate the denominator, which accounts for handling time. Multiplying attack rate, handling time, and prey density, then adding 1 gives 2. Finally, dividing 20 by 2 gives our answer. The spider eats 10 flies. Let us push this example further to see what happens if the food supply doubles to 40 flies. The spider's attack rate, handling time, and total time remain exactly the same. We follow the exact same steps, starting with the new numerator. Multiplying 0.1 by 40 by 10 gives us 40. The theoretical encounters doubled. Now for the denominator, representing the increased burden of handling time. Multiplying 0.1 by 0.5 by 40, then adding 1 gives 3. We divide our new numerator of 40 by our new denominator of 3. The final answer is approximately 13.33 flies. Even though the prey doubled, consumption only increased slightly. The spider is hitting its physical limit. We just saw in our example that the spider's consumption did not double, which brings us to an important mathematical proof. Why exactly does the consumption hit a physical limit? Let us look at Holling's disk equation and analyze what happens as the prey density, N, grows infinitely large. We are essentially taking the mathematical limit of the equation as N approaches infinity. In the fraction, both the numerator and the denominator contain the variable n. To evaluate this limit and find the horizontal asymptote, we can divide both the top and the bottom of the fraction by n. This is a standard algebraic technique that will reveal the absolute maximum number of prey a predator can consume. Continuing our derivation, let us simplify the fraction. After dividing by n, the n in the numerator cancels out, leaving just a times t. In the denominator, dividing by n gives us 1 over n plus a times h. Now we apply the limit. As n approaches infinity, the term 1 over n becomes vanishingly small, effectively approaching 0. This leaves us with a times t divided by a times h. The attack rate, a, cancels out from the top and bottom. We are left with a beautifully simple final result, t divided by h. This proves mathematically that the maximum number of prey a predator can eat is entirely dictated by the total time available divided by the handling time. Now that we have proven why the plateau exists mathematically, let us visualize it. On your screen is a graph showing Holling's 3 functional response curves. The horizontal axis represents the prey density, and the vertical axis represents the number of prey consumed per predator. Look at the straight line labeled Type 1. This assumes no handling time, so consumption grows forever. Now look at the Type 2 curve. It starts steep but gradually bends over, forming a flat plateau. This visualizes the exact mathematical limit we just derived, where handling time restricts eating speed. Finally, the type 3 curve is S-shaped, starting slow due to learning, then accelerating, and finally hitting that same handling time plateau. We've covered a lot of ground today, so let us summarize the key takeaways. First, remember that the functional response is all about the individual predator's appetite and physical limitations. Specifically, we saw how handling time prevents them from eating infinitely fast, creating a mathematical plateau. Second, the numerical response is about the predator population as a whole, growing through reproduction or migration when food is plentiful. Finally, by multiplying the functional response by the numerical response, ecologists can determine the total impact predators have on a prey population. You now have a solid understanding of the delicate balance that dictates the stability of entire ecosystems. Great job!